Hi, this is Chrisferb, and I'm going to review a chi-square test of independence. Okay, this is a common type of question set up for a chi-square test of independence, and I think it's a practical type of example. A complaint has been filed against a large company of age discrimination related to employees over the age of 50 being illegally terminated. You, as a human resource consultant, have been hired by the company to defend the company and defend its actions. As a first step, you need to perform a chi-square test of independence to determine if employees over 50 years old appear to be disproportionately terminated. The observed table of retained and terminated employees is listed below. Assume the likelihood of an employee being terminated or retained is equal, i.e. 50% chance of being terminated, 50% chance of being retained during the period selected. So what we have right here is I laid this out so that it saves a little bit of writing work here. We have the observed data. This looks pretty biased when we look at it right off the bat. And then we have the expected table, and this just saves us a little bit of time. Okay, so we have the observed data. So let's take a look at this. It says observed, and we have age. So less than or equal to 50, and then over 50, and then totals for both columns. So it says retained, meaning not fired essentially, and then terminated, meaning fired essentially. So retained, 90%. Let's say this is within a year's period of time. So 90% retained under 50 and 10% retained over 50 and then terminated. So the people under 50, it's 5 of them were terminated and then 95% over 50 terminated. Well, it's starting to look a little biased. And then we have the totals here. So there were 95 people that were under 50 and 105 that were over 50. So the totals are listed there. So for the expected, let's fill this in. For the expected, and I mentioned it right up here, let's say in a perfect world where age doesn't play into this decision-making process of terminating or retaining somebody, it would be 50-50, flip of a coin. It would be not based on age, so it would be based on something else, which would essentially say the age has nothing to do with it, and you would expect half of the people over, half the people under to be terminated and retained. So if we do the math and we take 95 people, employees, that are under 50, we would expect half of them to be retained and half of them to be terminated. And if we took 105 employees that were over 50, you would expect half to be retained and half to be terminated. So these numbers are 47.5, 47.5. And this is just half of 95 for each box. And then half of 105 is 52.5, 52.5. So we have our table filled in. Now I'm going to move to a different piece of paper because I just don't have space. So now we're going to continue this problem. Okay. So now to do this, what we have to do, which is very common with the chi-square types of problems, is we're going to compare the observed and the expected, and then we're going to determine if it looks different than expected. Okay, so what we do first off is we have our expected and observed right there. I'll put them on here so we can see them. So what we're going to do is we're going to work out our math. There's a couple things we're going to do. First, we're going to list the degrees of freedom. So the degrees of freedom for this question are like this. It has to do with columns and rows. And so it goes like this. Number of rows minus 1 multiplied by number of columns minus 1. And that gives us our degrees of freedom. So for this problem, it's a 2 by 2 type of table. So we have 2 minus 1 multiplied by 2 minus 1, which means 1, 1, 1. So we end up with degrees of freedom of 1. Okay, so we're going to need that in just a little bit. The other thing is, our formula for this problem is very common in the chi-square world. It's this. And it's the observed, expected, squared, and then expected. So that's a common formula for these problems. And then a couple other things to write down right off the bat. Let's see. Our hypothesis statement goes like this. H0, which is our null hypothesis, and then we'll say H1, which is our alternative. So H0 is always the status quo. So H0 would be that, let's see, say retention, which is a characteristic, say number 1. Say characteristic number 1 is independent of age, and then we'll say characteristic number 2. So we have age and then retention. So it's the table that has both the horizontal characteristic and then the vertical characteristic. And then the alternative hypothesis would be that it's not the status quo. Hence, we have a problem, which would be retention characteristic number 1 is dependent on, so now you see why we call it the test of independence. So is dependent on age, which is characteristic number 2. So the first one is the null hypothesis is it is independent of, test of independence. And then the alternative hypothesis is it is dependent, meaning these are there's some type of dependence on the other. Okay, so we have the degrees of freedom as 1. We have the formula, and then we have the null and alternative hypothesis. So now we just need to do the math. Okay, so the math isn't that bad. It's just kind of, like I said, it's very similar to what we've done with the goodness of fit test. So the math goes like this. I'll explain. So we have 90 subtract, say, 7.5. Once I draw this or have this all written out, I'll explain where I got all of the pieces for 7.5. Then we do plus. Then it is 10 subtract 52.5 squared and 52.5. So these values right here, see, this is the expected. So the expected is always, this value is always on the bottom. And then we do plus. So it's always 52, whatever this is, 52.5 will be down there. And then we do 5, subtract 7.5. And then 47.5 squared, and then we have the last part, 95 subtract 52.5 squared, and then that would be 52.5. Okay. So this is the way this works out. I'm just making sure I have the right information right now. I don't have enough room here, so I'll draw a little squiggly here. Okay. So let's take a look at the columns. Let's see. So the first one, make sure I'm on the screen. So for the first one, 90 subtract 47.5. So we have as 90 and subtract 47.5. The next one is 10 subtract 52.5. The next one is 5 subtract 47.5. And then 95 subtract 52.5. Okay, so we're matching up the same position in each table because we have to match up what's observed and what's expected. Otherwise, we can't do this test effectively. So our answer when we do all of this math right here is a pretty large number in the world of this. It is 144.8622, and this is called our calculated statistic. So that's our calculated statistic. Now we're going to go and find what our critical statistic is. And the critical statistic, we don't need a lot of space for this. It's this. And do a little explanation here. Degrees of freedom 1, comma, to a 0.05, which is the 5%. We're going to look at that value. So 1 to 0.05, a little bit small. So 1 to 0.05, 3.841. So 3.841, I'll back this out. So right off the bat, so that's our critical statistic. So our critical statistic is 3.841. Our calculated statistic is 1.44. And now we can draw this out if we want. Not a good artist, but you get the point. Let's put down our critical statistic. We'll say our critical statistic, should have actually drawn it back for this one, is say 3.841. Well, in this case, 144.86 would be way out here somewhere, but we'll just use this line that's already here. We'll say that's 144.86. So in that case, it is in our rejection zone, and if it's in our rejection zone, we reject, which means the null hypothesis, it appears that it's not true, or that we need to do more testing, which kind of means our status quo may not be what we thought, which in this case means if we reject HO, what it means is it appears there's bias, and it appears that people who are over 50 years old are being terminated and not retained as much as people who are 50 years old or younger. Let me make sure I have everything here. I believe I do. Oh, and then the last thing is we're going to do this on the calculator. So on the calculator, I already have it set up in the matrix. So what we do is we turn this on. I hope my matrix information stayed in here. I'm not sure. So what we do for the chi-square test of independence is we have to use the matrix editor. And so we do second matrix. I'm thinking it stayed. And we have A and B. And the way that the chi-square test of independence is set up is it uses the matrix A as the observed, and it uses the B as the expected. Now you can change these, but I'm just going to go and click on it real quick so you can see what the data is. So this is the A matrix, which is the A is the observed. So 90, 10, 5, and 95. 90, 10, 5, and 95. And then I'll show you the B. Oh, second quit. Do second matrix. We go down to the B. And so the B is 47.5. Then the 52s. So it matches the expected. Both 47.5, 52.5, and the 47.5, 52.5. Okay. So now let's go and run this on the calculator. And to do this on the calculator, what we do is, I believe, let's see, it's second distribution. Nope, it's not that one. It's actually in the stats. Okay. So you go to stats, and then go over to the right where it says tests, and then we're doing the chi-square test. It's not the goodness of fit test, it's just the test. And we have our observed being A, and then our expected being B, and then we go down to calculate. If you do draw it, we'll draw it out, but it's a lot quicker just to calculate. Okay, so the good thing is that our numbers match up pretty well. 144, 144.86 right here. And then our p-value, this is actually the p-value. Now, in this case, we're testing to a 5% critical value, and this p-value is huge. And because it's huge, we would actually, wait one sec. It's huge right here, but it's actually to the, it's actually the E negative 33. So the scientific notation, so it's actually tiny, I'm sorry. So we're going to reject, and then our degrees of freedom is 1. So remember with these also is sometimes the calculator will give this E and then a value here. What this means is I usually move this over 1. So we move that over 1 spot, and then we would put 32 zeros in front of the decimal point after we move it once, which is in front of usually the number that's there. So the p-value is really small, which means the probability of getting an error or by coming up with that data just by sheer chance is pretty small, which means we reject the null hypothesis. So that's how you do this on the Texas Instruments TI84, 83 variant, and this is how you do it when you write it out by hand. So thank you.